In the meantime, let me go ahead with the introduction. So, Professor Rahman did his PhD from Bergen University in Norway. After that, he went for a postdoctoral fellowship at Math Science and followed by another postdoctoral fellowship in Poland, the University of Gdansk. After that, he came back to Allahabad University in the mathematics department, and later on, he moved on to ISI Kolkata. With that, Ramij, please go ahead and the stage is yours.
Thank you, Chair, for nice introduction. I think my screen is visible. Now I am into
your screen is visible.
Presentation,
yeah, just
presentation mode. Yeah,
yes.
Everything is
Perfect.
fine. I think. Yeah.
Perfect. Okay. We can hear you. We can see your slides.
Okay.
Please
so let me check the slides are moving or not. Are you?
They are moving. They're perfectly moving.
Very good. Okay, let me thanks again to Professor Panigrahi and the organizers for organizing such a nice school conference in every year. It's a huge task, I know, so I appreciate them from my bottom of my heart. So let's start my talk. So today I prepare mostly for school talk. I try my best to reach the students as much as possible through this what is quantum cryptography and other tasks. Okay, so as you can see, the title of my talk is Quantum Cryptography Based on Measurement Inputs. So if you have any time, any questions, just write in the chat box. I can see the chat box. So you are free to ask anything. Okay. So move on the next slide. So this is overall outline of my talk. So I'll first tell you what is cryptography. Then I will go a little bit technical things. It's a non-locality test, but I will describe it in a game manner. So I don't think it will be very difficult to take it. And then it's some non-local features which are required to build the quantum protocols. Okay, then I will go for a generalized version and different protocol, how I can use this or whatever telecommunication, electronic communication used. Nobody can learn your text or your message. So this is the task. So in a simple way, you can say that you have Alice. Here you have Alice. And there is a receiver, Bob. Alice is a sender. So Alice used some encoder. So he modified that message or enveloped this message in such a mathematical, use some one-way mathematical function. So and make is unreadable. So it's called cryptotext. And then C, by reading C, you cannot get M unless you know the corresponding decoder key. So now Alice sent this through public channel, any communication channel. It can be courier, it can be email, it can be whatever, phone text, WhatsApp, whatever. So then when Bob received this C, only Bob have this decoder, so D, and Bob can decode the message. So this is the simplest way. Now the question is how Alice and Bob can generate corresponding E and D function, the encoder and the decoder. So Alice is encoding in one end and Bob is far apart from Alice. So Bob has corresponding decoder. Okay. So yeah, so this is one simple example. Okay, so bits cannot be reused for any future. The same problem arrives. So key bit must be delivered in advance and it should be secure until it's used. So this is the difficult. So you have to deliver in advance. So what is the way of delivering this securely, this key? So if you send by courier, or courier man can read that key by scanning your mail or whatever. If you use email, electronic email, one can hang your email. So creating this key in two different places, the same symmetric key, it's a main task. Okay. So there is no foolproof classical way to generate this key in two different places. So this is the main task here, to generate key in two different places. Okay. So there are classical protocol, as I mentioned earlier, that those are not foolproof. So Diffie-Hellman, so and RSA key, this Revist, Samir, and Alderman. So this is called RSA. These are two popular way you can have. You can send secret messages. So they are not. They are using public channel, and this is not a one-time key. This is they are using. They are creating this. The mathematical fact that you cannot factor a number. So you cannot factor in a number in means in a given time, in a finite time. You cannot always factor a large, very large number. Not if it has a smallest divisor, then you can easily factor. But if it has a very large divisors, all the divisors are very large, you cannot factor that number. So factorization problem. Based on this factorization problem, this RSA protocol and all those Diffie-Hellman, it's a discrete logarithm problem. It's like similar problem, classical problem. So these are the problem that with a finite time, you cannot solve those problems. Using those difficulties, your key is secure. So let me explain one of the protocol, mainly because RSA is very popular one. So I describe this RSA protocol. So the RSA protocol is like, you have two parties. So Alice want to send some message to Bob. Now the task started with Bob's. So Bob select two primes P and Q, which are very large. So you can see if you have a binary representation, it should be larger than 512 bits each. So you can imagine how big those numbers. So you can always select. And multiplication is not that much difficult. If you have a good computer, you can easily multiply. I mean, it's not a very difficult task. So now B, first select these two very large primes P and Q, okay, and calculate this n. N is equals to P dot Q, and every number has a Euler phi function. What is Euler phi function? Euler phi function is that number of integer which is less than that number and co-prime to that number. So for example, if you have a 5 is a prime. So number of Eulerian phi function, this A is 4, because 1, 2, 3, 4, all 4 are co-prime because it's itself is a prime. So any number is a co-prime. So number of integer, which is positive integer, which is less than 5 is 4. So that's why the Euler phi function for 5 is 4. Okay. You can take another example like 6. So then you have a Euler phi function like 2. So okay, so 1 and 5 are two functions which is co-prime to 6. So co-prime means you don't get the greatest common divisor is 1. Okay, between these two numbers. Okay, they are not, each of them are not individually prime, but the GCD, greatest common divisor between these two numbers, is 1, then it's called co-prime. Okay. Now, if you have two product of two primes, the phi function is defined P minus 1 and Q minus 1. As I see, mentioned that for a prime, it's if P is a prime, then P minus 1 are the number of positive integer which is less than P and co-prime to P. So you have two P and Q, and there is a theorem, so you can easily prove that also. So phi n is equals to P minus 1 and Q minus 1. Now this Bob select a E. this E, randomly select a E, which is the GCD of E with Euler phi function is 1. That is co-prime to this Euler phi function E. So randomly select a number. It's a random. Now Bob calculate this D. If Bob knows this P and Q, Bob can calculate this inverse with respect to Euler phi function. So D, Bob can calculate that D. Okay. Hello. Yeah. Sorry. Just a minute. Sorry. Okay. So Bob can calculate this D. So E and D calculated by E is randomly selected and D is calculated. Now Bob make public or send to Alice through any public channel N and E. So D is secret. D and PQ all are secret. So nobody, only Bob have that information. No other third party. Even Alice does not have any information. So Alice now received this N and E. Now Alice have a message M. Now Alice applied this E mod N, but in this way. So Alice calculate the ciphertext C is equals to M to the power E mod under mod N. So N and E are available with Alice. Not only Alice, everybody knows this. So now Alice want to send this message M. So Alice calculate this C, which is equals to M to the power E, and sends the C to Bob. Okay. Now Bob decrypts this by computing M equals to C to the power D, because D is already in Bob's hand. Bob already calculated this D. So under mod N. So nobody have this D unless they have information about P and Q, because it's a very difficult to calculate P and Q. If anyone have this P value of P and Q, he or she can also calculate D, like Bob. Okay. So we are assuming that this factorization problem is very difficult. So based on that, so that's why we choose this number of the large primes. P and Q are very large, which is larger than 512 feet. Okay. So how this CD equals to M, you can easily calculate that with a Fermat-Little's theorem. So C to the power D is nothing but C is M to the power E to the power D mod N. So it is a ED. Now there is this theorem. So K phi N plus 1, because phi N ED equals to, if you see. Okay. So am I audible? Because some disturbances happened. Sorry. Hello. Hello.
Yes, you're audible.
Okay, it's fine. Okay, so what are the difficulties of this type of one-time paid key? So this type of key is called one-time paid key. So it is secure only when the number of key bits is at least as large as size of the message. Because if you reuse this string, you have a small string, and if you reuse it for a large string, then there are some guessing attack possibly. So you have to have the key bit string as long as at least as large as the size of the message. Okay, the key bits cannot be reused for any future. The same problem arises. So key bit must be delivered in advance, and it should be secure until it used. So this is the difficult. So you have to deliver in advance. So what is the way of delivering this securely, this key? So if you send by courier, or courier man can read that key by scanning your mail or whatever. If you use email, electronic email, one can hang your email. So creating this key in two different places, the same symmetric key, it's a main task. Okay. So there is no foolproof classical way to generate this key in two different places. So this is the main task here, to generate key in two different places. Okay. So there are classical protocol, as I mentioned earlier, that those are not foolproof. So Diffie-Hellman, so and RSA key, this Revist, Samir and Alderman. So this is called RSA. These are two popular way you can have. You can send secret messages. So they are not. They are using public channel, and this is not a one-time key. This is they are using. They are creating this. The mathematical fact that you cannot factor a number. So you cannot factor in a number in means in a given time, in a finite time. You cannot always factor a large, very large number. Not if it has a smallest divisor, then you can easily factor. But if it has a very large divisors, all the divisors are very large, you cannot factor that number. So factorization problem. Based on this factorization problem, this RSA protocol and all those Diffie-Hellman, it's a discrete logarithm problem. It's like similar problem, classical problem. So these are the problem that with a finite time you cannot solve those problems. Using those difficulties, your key is secure. So let me explain one of the protocol, mainly because RSA is very popular one. So I describe this RSA protocol. So the RSA protocol is like, you have two parties. So Alice want to send some message to Bob. Now the task started with Bob's. So Bob select two primes, P and Q, which are very large. So you can see it's a, if you have a binary representation, it should be larger than 500 bits each. So you can imagine how big those numbers. So you can always select. And multiplication is not that much difficult. If you have a good computer, you can easily multiply. I mean, it's not a very difficult task. So now B, first select these two very large primes P and Q, okay, and calculate this n. N is equals to P dot Q, and every number has a Euler phi function. What is Euler phi function? Euler phi function is that number of integer which is less than that number and co-prime to that number. So for example, if you have a 5 is a prime. So number of Eulerian phi function, this A is 4, because 1, 2, 3, 4, all 4 are co-prime because it's itself as a prime. So any number is co-prime. So number of integer which is positive integer which is less than 5 is 4. So that's why the Euler phi function for 5 is 4. Okay. You can take another example like 6. So then you have a Euler phi function like 2. So okay, so 1 and 5 are two functions which is co-prime to 6. So co-prime means you don't get the greatest common divisor is 1. Okay, between these two numbers. Okay, they are not, each of them are not individually prime, but the GCD, greatest common divisor between these two numbers, is 1, then it's called co-prime. Okay. Now, if you have two product of two primes, the phi function is defined P minus 1 and Q minus 1. As I see mentioned that for a prime, it's a If P is a prime, then P minus 1 are the number of positive integer which is less than P and co-prime to P. So you have two P and Q, and there is a theorem, so you can easily prove that also. So phi n is equals to P minus 1 and Q minus 1. Now this Bob select a E. This E randomly select a E which is the GCD of E with Euler phi function is 1. That is co-prime to this Euler phi function E. So randomly select a number. It's a random. Now Bob calculate this D. If Bob knows this P and Q, Bob can calculate this inverse with respect to Euler phi function. So D. Bob can calculate that D. Okay. Hello. Yeah. Sorry. Just a minute. Sorry. Okay. So Bob can calculate this D. So E and D calculated by E is randomly selected and D is calculated. Now Bob make public or send to Alice through any public channel N and E. So D is secret. D and PQ are all are secret. So nobody, only Bob have that information. No other third party. Even Alice does not have any information. So Alice now received this N and E. Now Alice have a message M. Now Alice applied this E mod N, but in this way. So Alice calculate the ciphertext C is equals to M to the power E mod under mod N. So N and E are available with Alice. Not only Alice, everybody knows this. So now Alice want to send this message M. So Alice calculate this C, which is equals to M to the power E, and sends this C to Bob. Okay. Now Bob decrypts this by computing M equals to C to the power D, because D is already in Bob's hand. Bob already calculated this D. So under mod N. So nobody have this D unless they have information about P and Q, because it's a very difficult to calculate P and Q. If anyone have this P value of P and Q, he or she can also calculate T, like Bob. Okay. So we are assuming that this factorization problem is very difficult. So based on that, so that's why we choose this number of the large primes. P and Q are very large, which is larger than 512 feet. Okay. So how this CD equals to M, you can easily calculate that with a Fermat-Little's theorem. So C to the power D is nothing but C is M to the power E to the power D mod N. So it is a ED. Now there is this theorem. So K phi N plus 1, because phi N ED equals to, if you see, how do you calculate this ED? ED equals to 1 mod of phi N. So that means 1 plus K phi N. ED equals to 1 plus K phi N. So we have used this K phi N plus 1, ED equals to. Okay. So now you can rearrange this and simplify it with this. Now phi M to the power phi N is equals to 1. So 1 to the power K is 1. This is Fermat-Little's theorem. So you get N. So now Bob have this message M. Okay. So you can take a simple examples. So choose this PUM for giving this. These are not obviously very large prime, but to check that how this protocol works. So P equals to 7 and Q equals to 17. Now if you calculate this n equals to pq, which is equals to 119, and the phi function is equals to 100 of 19 is equals to 96, because it will be 6 into 16, so it will be 96. Now Bob select randomly E is equals to 5, and GCD of 5 and 96 is 1. So as this Bob now selects this P equals to 7, Q equals to 17, calculate this N 119, calculate the phi function 96, equals to randomly selects E, and which is co-prime to 96 obviously, and you can determine this D is equals to 77. So you can also verify that ED equals to 1 mod 96. So E is 77. Now this 119 and 5 is sent to Alice through public communication channel, and Alice calculate the C, which is equals to P is the message. You can take P is the message. So P to the power 5 mod N, and decryption is happened with C to the power 77, because we have seen that this is equals to P. So Bob have this message P, plain text. So that's it, the RSA protocol. Now this you can see the important all the security based on this n equals to p dot q, which is equals to 119. So choosing this p and q is the main task, or choosing an n is the main task. So presently this is called RSA number. So this is 2048 bits RSA number. So this number is a factor of two large, this is a product of two large primes. Okay, so if you are able to solve this, you can win a prize. So it's available in the internet. You can see that problem. So this is you can see how big these numbers, these are called RSA numbers. So this is your n. Now you have to find this p and q. Okay. So possible attacks, as we already discussed. So if you are able to factor in, then the security is gone. So security mainly based on computational hardness, not any physical law. So if we have quantum computer, we already have the algorithm for quantum computer, quantum algorithm for factorization problem, but we need a proper computer. Yes, IBM and all those people are claiming that they are able to factor, but it's a very small numbers, not that big one. So it's still the actually useful quantum computer is still not not available. We have to wait at least some years more. So if you have quantum computer, you can easily break all this RSA and Diffie-Hellman problems. So what's the possible solution is quantum cryptography, because it's not, the security of quantum cryptography is not based on hardness of any computational task. It's based on some physical laws. If you believe in quantum theory, then you have a secure quantum cryptography. Okay. So to go into quantum cryptography, as I mentioned in the starting of my talk, that we need some sophisticated or technical tools to build the cryptography, secure cryptographic system. So I used these tools, which is little bit not so convenient or so well known things. So this is some kind of, I think you have, if you attended so many lectures, and every time you heard about Bell test, Bell inequality, Bell non-locality. So what Bell inequality does that that you have some quantum feature which is not present in classical world, which is not present in how fast can quantum computer break RSA algorithm? Okay, it's because that's a not very easy to answer. It depends on your protocol, because we believe if you have polynomial time. So this is I'm answering in the chat box. So if you have an algorithm which takes polynomial time, then you can do it in a finite time. So still we have to work, because if it's polynomial time and use very large time, it's again difficult. So polynomial time is main goal. It's not even polynomial, it should be in a linear or quadratic at least, then it is quite useful, otherwise not. But we already have polynomial time algorithm. Okay, so we don't know exact time. I can't. It's actually it's something like e to the power x and log x and log x and x 10x, or you can say e to the power x and 10x. So which one is increasing rapidly increasing in certain interval? 10 to 10x is give you more value, but in if you go in a larger scenario, e to the power x will grow exponentially. So it's like that. Quantum computer useful for very hard problem, not for small, like if you want to factor 10, it will not be very useful, because you have to do a lot of things in quantum computer. That I think. But exact time we don't know. We have to. It should be a polynomial time, obviously. Otherwise, it's not meaningful. Hope I answer your question, this Ramesh Kumar. Okay. Now come back to this Hardy's paradox. So as I discussed that this is a kind of Bell test. So what Bell does? Bell does it's uh, Bell distinguish this classical feature and quantum feature in some sense. So that means there are some non-local realistic feature inside quantum theory which Bell can reveal. But so Bell proved that no local realistic theory can reproduce quantum theory. Yeah. So that means you have, for example, entanglement have some non-locality feature, non-local realistic feature. So this is also a similar kind of proof, but it's not going to go in very large calculation or expectation value. It's a little bit logical, as I can say. So local realistic theory means locality. What is the locality principle? So locality principle is if the measurement choice of one side, like here Alice, the choice of measurement in Alice, the choice of inputs, so I can say in general, the choice of inputs is Alice cannot influence immediately cannot influence the outcome of the form. Okay, so this is the locality principle. So how this Hardy paradox runs? So you have two parties, Alice and Bob's. They are sitting in two different planets, and the distance you can take as a one light year, or even larger. So they have some black box inside. So Alice have one black box, Bob also have one black box. Okay. Okay, there is another question: which is more efficient for long distance key distribution, continuous or discrete? Oh, okay. So it's again depend your system, your environment, in which way. So still it's I don't think it's a very easy answer. Still it's research is going on. As far as I know, I don't know actually which one is at this moment. This Priya Majumdar questions, that which one is more efficient, the long distance key distribution, continuous or discrete? I don't know. At present, I don't have answer. Okay, so come back to this Hardy paradox. So you have two system, Alice and Bob. So Alice have a black box and have two switch U and T. Bob also have two switch U and T. And if you press one switch, Alice or Bob press one the switch of their individual box, they will give binary outcome. You can map it 0, 1 or +1, -1 or red light, blue light, whatever, right? So the inputs is binary, outcome is binary. Now I am putting a joint probability condition on this systems. So I am saying that if Alice and Bob randomly pressing this button, so sometimes they will choose, both of them have chosen U. So Alice have chosen U1, Bob have chosen U to switch. Then their outcome, there are 4 possibilities. So plus, 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 minus, minus, plus, and minus, minus. So then their outcome, both of their outcome is plus, plus is this probability Q. So I'm putting this restriction. So these black box behave in such a way. They are not communicating each other, but they have previously correlated in such a way that they are behaving like this. Okay. So the second condition tells that if Alice have chosen U and Bob have chosen D, they will never come up with, both of them will never come up plus plus. It can be plus minus minus plus minus minus, but it will not be plus plus. Similarly, the third one is if Alice's input is D, Bob's input is U, then both of them will never have plus plus outcome. And the last condition is if both of them have their input D, then they will not end up with minus minus. Okay. So these are the 4 joint probability condition. Now see, if you have restricted a local realistic manner, so if you see that what is the difference between first 2 conditions, only you can see this, only you can see that only you have just a minute. I think I should take that pen, then that will be more. Yes. So only you can see this part is different. If you look these 2 question, only this part is different. So instead of U, if Bob choose D, they will never end up with plus plus outcome. So what will be the conclusion in a projective way? What should be the conclusion? It should be D2 should be, if you have restriction, local realistic restriction, that you don't have any influence. The choice of inputs on Alice's side have no influence on the Bob's output. So D2 always should be -1. So this is my conclusion. Similarly, if you go these two, sorry. So what's the difference between first and this? So D1, if the first equation is, this is true, if this equation is true, if this equation is always true, then what is your conclusion? Your conclusion is that D1 should be -1, at least for those Q times, at least for those Q times. Now you have at least Q times, you have this, which is contradicting this fact. They will never come up. So if you, why we get this contradiction? Because we have used this local realistic theory. Okay? So, but you have a quantum solution. So that means quantum correlation or quantum theory cannot be reproduced by any local realistic theory, or in other words, you can say as a classical theory. So now how you can calculate this quantum states, which or correlation, which can show your this 4 joint probability condition. Okay, so here this P of A, B given X, Y is calculated this manner. So X, Y is your inputs. So X, Y is your input. Okay, there is one more question. How is Hardy's paradox different from Bell's inequality? Okay, so Bell's inequality and goal of Bell's inequality and Hardy's paradox are same, as I mentioned. The difference is in a Bell's inequality, you have to calculate a lot of expectation value. Here, it's like joint probability. It's kind of logical, nothing else. And another major difference, Bell give you maximum value in a singlet states. So 2 root 2, you are achieve the maximum Bell violation in a singlet states, and no singlet states is going to give you Hardy's paradox or Hardy's. Yeah, no maximally entangled states or Bell states can give you this kind of joint probability distribution. These two are major difference. There are another difference that instead in a Bell scenario, you are calculating just one parameter, the bound of that inequality, like 2 root 2 or whatever, larger than plus minus 2. But here you are actually working in a joint probability. So you have 4 conditions. So in a parameter wise, this is more, you can check more power. Okay. In that sense, like you can manipulate one parameter, but you can inside you also have to have manipulate the joint probability distribution. So if it is not a very superior, but at least it's equivalent to Bell test in a security sense. Security sense means, okay, in a third party is managing, giving you some influence, so that's why you are getting Bell violation. It's your correlation is not actually the entangled states. So in that sense, if you want to check whether there is a third party influence, or actually a genuine correlation, entangled states giving this Bell violation. So in checking that process, it's at least it's you can see it's better in some sense. I don't have any proof, but here you have to manage 4 parameter where you have to manage only 1 parameter. So I'm not saying it's superior, but at least it's the same level. But the Bell cannot be superior in that sense, because Bell only have 1 parameter. In Hardy you have 4 parameter. But that's a different thing. It's a part of the device independent task. But what you can see that maximally entangled states don't show Hardy paradox, where maximally entangled states gives you maximum violation, and it's a similar kind of a logical proof, not like you have to calculate that expectation value, as you can see. So now come back to this point, this Hardy's paradox. So now we want to calculate that joint probability A B given xy. So this is like x equals to A. So x is the operator. So matrix is a Hermitian matrix. So you have eigenvalue, real eigenvalues. So these are the eigenstate corresponding to eigenvalue A. These are the eigenstate y of B equals to, these are the eigenstates corresponding to the eigenvalue B. So now you have to satisfy this 4 joint probability condition. So first condition, it means this the corresponding product states which have to, if your psi is a quantum states, that state should be non-orthogonal to this product states. That probability means, because you see this is the calculation. So u1 equals to +1, u2 equals to +1, and the psi should be in the inner product of psi should be non-zero. Inner product of psi should be non-zero with this phi 4. Similarly, you have t1 equals to +1 and t2 equals to +1. So your psi must be orthogonal to phi 3 to get this probability one, this one. Okay. And also it should be orthogonal to phi 2, it should be orthogonal to phi 1, and so on. So you have 4 product states or 4 vectors in a 4x4 system. In a 4x4 system, okay, so what's happened? I don't know. It's not moving. Oh, I don't know. My internet is slower. Now this is your dimension. If you are in a qubit system, your dimension is 2 × 2. So now you have 4 vectors or 4 states. Now you can rearrange this u d basis in the basis of u in this manner. So, and this is the normalization condition. This is the non-commutativity condition. So to make u and d are non-commutative on each side, then you have to have non-trivial values of aj's. Now with this parameterization, you can easily check that phi 1, phi 2, phi 3, phi 4, these four-dimensional vectors, four-dimensional vectors are linearly independent with these restrictions. Okay. Now, any subset of the linearly independent set is also linearly independent. So if you take phi 1, phi 2, phi 3, you have total dimension 3. If you will take a span of these three linearly independent states, your dimension is 3. So your total dimension is 4. So you have only one state left. So that means it should be a pure unique states. So this is another proof, another difference with the Bell. So you only a unique for a given set of choice of observables, only unique Hardy states can show this Hardy's paradox. Where you have for Bell violation, it's not. Maybe the unique, the maximum Bell violation, you have a uniqueness, but overall you don't have that uniqueness. So 2 root 2, there are a lot of states can violate Bell inequality, can give you Bell value. But in Hardy paradox, only for whatever value of Q, it's a non-zero value, then only a unique for a given set of local observables. Only a unique Hardy states. So uniqueness is very important here. So how do you calculate this psi, which is going to satisfy this Hardy paradox? It's quite easy. You have four linearly independent states, and that state should be, and the Hardy state should be orthogonal to phi 1, phi 2, phi 3, and non-orthogonal to phi 4. So Gram-Schmidt orthogonalization process, you can make an orthogonal set, and your psi is nothing but phi 4 dash. The last orthogonal states of the Gram-Schmidt orthogonalization process. Okay. And if you calculate your Q is this quantity, you can easily check that inner product with psi, and inner product between psi, this is the Hardy states, and phi 4 is this. And if you take maximization over all parameters, you will get this value 0.09. And in the maximum case, if you reach the maximum value, it's a not only a unique states, it's a self-test, device independent self-test. That means if you go higher dimensional system or more multipartite system, and if you don't believe the internal working of the devices, the measurement devices, and you get this value with all those other 3 0, joint probability is 0, and that non-zero probability is 0.9, then it automatically says that this is the exact 2x2 Hardy states corresponding to these maximally entangled states. So you don't rely on the device, still you have that. If you have a high dimensional system, it's actually that maximally 2x2 system with a tensor product of the rest of the system. So it's a device independent self-test if you have key equals to 0.09. Okay. Now you can extend, it's a 3-qubit system. So now you have a 3-party system. So each party have UD. And now I make it instead of plus minus 1, I make it a binary 0, 1. So first condition, joint probability condition, says that if all of 3 players choose inputs U, and all of them have 0 outcome, it's a 0 probability Q, which is non-zero. And if ith party choose U and jth party choose D, and I not equals to J, so this is a marginal probability, and they will never end up with 0, 0. This is the condition. So I can be 1, J can be 2, I can be 2, J can be 3, I can be 3, J can be 1, all possibilities are there. And the last condition, again, you can see this contradiction. So this is again, you can no local realistic theory can satisfy these conditions, but quantum have solution. So I, again, like previous case, I have make this product states. So the states which is going to satisfy all these conditions must be non-orthogonal to these states and orthogonal to all those states, product states. And again, if you see the span of this states, these are to the power 3 minus 1, so only one dimension is left, so again you have a unique Hardy states. So you can extend its n party and you have this uniqueness. Okay. And here we have calculated this maximum value is this for these Hardy states, and here is actually they are equivalent. All the three internal angle between U and D are same. This implies this means. Okay. And you can again find the Hardy states which is in this form, like this Grant-Smith orthogonalization process, and you can build a 3 device independent self test for this maximum violation, like similarly like other case. And as I mentioned, you can go in higher dimensional. So now I have taken not qubit system, it's a dit system. So it's a n dit most general, so up to n party and d1 d2 dn in outcomes, and if you have this type of conditions, and again you can have a genuine entanglement in the case. And other thing is that only genuine entangled states is going to satisfy. Means it's not, you cannot bipartite the entanglement, entangled correlation. Only genuine entangled satisfy all those correlations, like previous correlations also. Okay, so you can have a more general version. Now I don't require much that. Okay, so how much time do I have? The chair.
I think we are about time, but you can always take 5 minutes more.
No, I think I started 20 minutes late. No, possibly.
I see.
12:20.
You started at 12:20. Okay, fine. So please go ahead. I think now it's 12:05.
Yeah, okay.
Maybe you can continue for another 10 minutes and take questions for 5 minutes.
Okay. Yeah. Okay. So
yeah,
now I'll show how you can use that all those Hardy's paradox or Hardy's correlation in cryptography. Okay. So now you have Alice and Bob, and they are shares this Hardy states, this psi, many copies of psi, Alice and Bob sharing. So after sharing all those copies, they can randomly select some of the copies and they can perform Hardy test, or they can do it in the protocol itself and verify whether all the correlation are genuine. So those states who they have already used in the checking process, they just discard those states, and rest of the states they will have that they can generate the keys. Okay. So next, they in every case they were randomly picked one of the measurement operator and perform a measurements on their respective qubit. Alice and Bob does the same things. Now after performing all those measurements, as I mentioned, they now can randomly select some of the states and reveal all the outcomes and measurement inputs and verify whether this Hardy's paradox is satisfying or not. And for rest of the system, they use for key. So to do that, but they reveal. So this AFI like BB84 protocol, ACAT protocol, and all those other protocols. So when they perform measurements, they reveal measurements choice. That means input, not the outcome, measurement outcomes. Here, Alice and Bob publicly discuss this only the outcome, not the input, measurement inputs they have randomly chosen in the process. So all the outcomes is available. Now, from that outcome, they only select when they have plus outcome. When both Alice and Bob have plus outcomes. Okay. So if you remember, so this is the Hardy paradox. So when they have plus outcome, the measurement inputs cannot be anti-correlated. So U cannot be possible for plus outcomes. For Hardy correlation, this is also important. if you, so this probability, joint probability distribution is not present in the, so plus plus outcome, there are four possibilities: UU, UD, DU, and DD. So these are four possible inputs. So these two are already discarded. So only UU and DD are there. So these are non-zero probability. So that means when they have plus plus outcome, because outcome is now open, they already have measurement inputs is correlated, and they didn't reveal the measurement input. So that means they can generate. So you can map 0 and D can map 1, and they have key. So as in the beginning of the talk, we see that the creating binary string is the important task in two different places. So you have correlated inputs, so that automatically imply that you have generated key. And if you go for a device independent key, then you have to choose the correlation in such a way that its Q value is like 0.09. So it's quite simplest way you can have a quantum key distribution protocol which has as device independent security proof. Okay. So now you can go other cryptographic protocols like ladder detection, Byzantine agreement. So I'll talk few of them. Oblivious transformation, signature, digital signature, and all those things are there. So lie detection problem. So it's like it's a quite important in a network system. So if you in a network systems, there are a lot of nodes. For example, in your computer, there are circuits, and circuits have a lot of nodes. Now, it's obvious that all the time all the nodes are not working well. So with a minor default, it should not be your computer should not not working. So it should be reliable. It should be sustained with few nodes if few nodes are defaulting. So the task is this. For example, you have three different nodes. So one node is receiving the same information from two different nodes. So for simplicity, we have taken the C is the receiver, A, B, these are other senders. So Alice C is receiving the same message directly from node A, and the same message via B. Now C is checking whether these two messages she received, one should be same. If the same, C is going to forward that message. But it's a faulty device. So either A, instead of sending same message to C and B, may flip the message or send two different messages, or B is the faulty. Whatever received from A, B is flip that message and send to C. Now the C's task is who is faulty, A or B. That means see which message she should accept. She should accept. So this is the liar detection problem. It's now C's task is to find the liar. Who is the faulty, A or B? Okay. So again, there is no classical solution. Obviously, this if C equals to C not equals to M of AC not equals to M of BC, then A or B is liar, one of them. If both of them liar, we are not considering that because we only considering few nodes. So in the three nodes, only one node is faulty. So if you take A and B are faulty, then your protocol is not working, because if major default is there inside, then your computer is not going to work, or any network system is going to collapse. Okay. Again, so as I mentioned, no classical, but quantum solution is there. So we can also have a quantum solution with this hard disk correlations. So now you have three nodes A, B, AC, and BC. So each this A, B, AC, and BC, all these three connections shares this hardy states. Okay, large number of hardy states. Except C, no one has the knowledge about the sequence of the correlation. So C prepares all the hardy correlation, and C share between C and A, C and B, and A and B, and only C have that information which state is correlated to whom, and all those things. Only C has that correlations. Now C prepares a list LB, which is some information about correlation between A and B. So by knowing this LB, Bob knows at least that at least few qubits is correlated to Alice. Alice's which qubit means have not information about that correlation. So okay. So neither B or C reveals the information LB to A. So C prepares this LB and send to Bob. So Bob have that information, partial information, not all the qubits between A and B, but partial. Okay. So this is the scenario. So now they all of them perform randomly, choose one of the measurements U and D, U and D, U and D, and they now Alice perform measurements U and D and communicate the measurements outcome to C, and C also can easily check by these correlations, because C also perform these measurements and check whether which probabilities appear. So if by looking this, C can get that message, the measurement choice, because this Hardy correlation tells that. Okay. So now C already have this message, B also have that same message. The action by B measures qubits LB in a random basis UD, and B can easily figure out the message of MA, which message again with these conditions. And B may measure rest of his qubit in the message basis and sends to C. So now again C can easily verify with this Hardy condition what is the measurement basis, either U or D, as the measurement basis is going to be. Okay, so with Hardy condition, C can easily find the what's the measurement basis of Alice, what is the measurement basis of Bob, and she can easily, because Alice have no option to cheat to C, and Bob also have no option to cheat to C, because it's Hardy correlations can't do them. So if C has all the outcomes, then C can read the message. Okay. So and C can easily verify who is liar. Similarly, the Byzantine agreement. So this is a superposition of two liar detection problem. You can see. So instead of only one receiver, now B and C both are receivers, and B and C both supposed to receive the same message directly from A and via other. So B is going to get the message directly from A, and the same message via C. C also have the same, have to get the message directly from A and via B. And if you have two liar detection problem, and if you one liar detection problem where you can take C as a receiver, and one liar detection problem where B can as a receiver, then if you superpose these two, then I think you have the Byzantine solution. Okay, so that's it. I don't think I should go further because it's already 15. So I think, yeah, I should stop here. So that's it. Okay, thank you for listening. If you have any question.
Thanks, Ramij, for the wonderful talk. So time for questions. Maybe are there? I cannot see. Are there questions in the chat box which you would like?
Yeah,
to
I think couple of question is there. So
you already took some, right? I think maybe
yeah, few more
yeah.
are there. So
please
does
go ahead.
qubit provides any advantage over qubits? Okay, no. It's obviously qubits is simplest one, but if you want to generalize the system, you have to consider qubit. So we can generalize this system, this Hardy's paradox. So that's it. Because if you have larger system, obviously qubit is more used. Handle qubit sometimes it's more easier. I don't know. It's but always people are looking the protocol with simple systems, not very large system. If you have any advantage with QDIT, then you can go for that. For that, you already have a Hardy paradox or Hardy correlations. Okay, is this a better key rate than other device independent key distribution protocol? It depends on the security proof. If you say it's a fully device independent security, that means if you consider coherent attack, then this protocol is best. But the problem is, when in ideal case, the key rate is quite high, but it's not very sustainable or very useful if you have noise. Then the Vazirani protocol is superior if you have any noise. But in ideal case, our protocol is superior. Okay. The one another thing, the difference is, if you see the security attack, so it's like choice of your input, you are choosing your own. It's like reading your mind. So I think it's very difficult, and the outcome is coming out through some device. So attacking that outcome is more easier in that sense. It's a common man logic. It may be equivalent in a scientific way, but in a common man language, you're reading your mind and reading something which is come out in a device which is supplied some adverse party. It's a very difficult, it is very easy to attack that one compared to reading your mind. So our protocol, in some sense, it's to attack this protocol, you have to have read your mind. Means obviously the reading in mind means you have to attack the random number generators, because you are randomly choosing these inputs. I think I answered your question. Any questions? Anything?
If anybody else has question, please unmute and ask. Okay. If not, I think if you have further questions, I'm sure Professor Rahman will be happy to receive your emails regarding whatever confusion you had during the lecture. Thanks, Ramij, again for the wonderful talk. And hopefully next time, we'll host you physically because you are really next door. With that, I conclude this session and we reconvene.
Thank you very much.
Yeah, thanks. And we come back again at 3. So I hand it over to the organizers now.
Thank you, Professor Rahman, for such a nice talk. And thank you, Professor Das, for moderating the session. We'll start again from 3.